Okay, so this is an adiabatic compression. And the deal with adiabatic compressions is that no heat flows in or out. So our Q is 0 for what it's worth. We'll use that later, okay? But the first thing it asks us is to find the moles of gas. And I believe at point B, they tell us the pressure, the volume, and the temperature, right? So remember, the ideal gas law is PV is nRT. So therefore, N is PV over RT. Okay, so let's do that. At B, we've got 9 times 10 to the 5th. Our volume is 2E minus 3. I'm just reading it here. We can also read it off the graph too, right? 9 and 2. R is still 8.31. And T, it tells us that that's 850. Okay, so let's figure this out. 9E5 times 2E minus 3 divided by 8.31 divided by 850 kelvins. And we get that it is 0.25483 moles. And I'm going to store that because I'm going to use that later. Okay. And then it says, what pressure did it start at? And it looks like it started at just above 1, right? So what is that? And to do that, we're going to use pressure volume to the 5/3 is pressure volume to the 5/3. Okay? So what is the pressure at point A? Okay, so we know that we're going to do, the thing we know is at B, right? So we're going to go 9E5 times 2E minus 3 to the 5/3 equals, and then we don't know the pressure at A, right? But we do know the volume is 7 times 10 to the minus 3rd, right? To the 5/3. So we don't have to figure out the volume, we're going to figure out the pressure, which is good because solving for the volume is just a little bit harder, right? Okay, we can do this. 9E5 times 2E minus 3 raised to the 5 divided by 3, then hit the forward arrow. And then I'm going to divide by this guy, 7E minus 3. Oops, slight difference there. Raised to the 5 divided by 3. This is where you got to love these new calculators. And I get that it's 111,548.1663 pascals, right? So let's see, 1, 2, 3. So you'd say 1.12 times 10 to the 5th. That's where that answer comes from, right? 1.115 times 10 to the 5th pascals. Or 1.12 would be 3 sig figs, right? So what's the temperature at point A? Well, we now know the moles, right? So temperature is going to be, what is it? It's going to be PV over NR, okay? So for C, temperature is PV over NR. And now we know the pressure at that point, right? So the pressure is 111,548.1663. Our volume is 7E minus 3. We're going to divide that by the moles. We figured out 0.25483. 0.25483, yeah. And then R is still 8.31. All right, we can do this. We have the tools, we have the technology. Okay, so the number I've got on my calculator times 7E minus 3 divided by the moles divided by 8.31. And I get that that's 368.72866 kelvins, approximately, right? 369 kelvins, right? Okay, so now it says calculate the Q, delta U, and work for this process. Well, I'll tell you right now that Q is 0 because it's adiabatic. That's what that means, okay? That heat doesn't flow in or out. So we got the Q, right? Work would require calculus for this, and this would be negative work, right? But let's figure out the delta U. So delta U is 3/2 N R delta T, and we can figure out the delta T because we now have the temperature at the end or the beginning of the process, right? Okay, so that's going to be, and we have the moles, right? 3/2 0.25483. That's the answer we got here, right? R is still 8.31. And then our change in temperature is final minus initial. Okay, so final is 850. Minus initial is 368.72866. That's this guy. I'm just going to use numbers on my calculator, right? Okay, so 3 divided by 2 times the number of moles, which is right there, times 8.31 times final minus initial. So it's 850 minus the answer I just got. And I get that it's 1528.7. Okay, so delta U is positive 1528.7, which is about, really I'd have to say 1530 with 3 sig figs, right? Okay, it's a positive 1529 joules, which really is about positive 1530 joules, is really what we should say, right? Okay, now it says, let's see, we want to figure out the work done by this process. Well, remember that Q is delta U plus work. Well, Q is 0, so we put in a 0 for the work, for the Q, and that equals positive 1529. Just pick this, right? So we know that the internal energy increases by positive 1529. Therefore, the work done has to be negative 1529. And you know that pushing a piston in is negative work. The gas is doing negative work. That is, we're doing work on the gas. Okay? So therefore, our work is negative 1529. So all that happened here, really, was that we took this gas and we adiabatically compressed it. So we did it really quickly. And I'll demonstrate that in class, or I have already demonstrated it. And when that piston comes in, it hits those gas particles and speeds them up because it's moving toward them, right? And it increases the temperature. All right, did we answer all the questions? I think we did. All right.